Hello, tensor friends. We're back here with another riveting tale of the Gaussian curvature tensor. This time we're going to find the damn thing. Uh, it's been a long trip, but I tell you, I've learned a lot. I hope you have. This time we're going to find the Christoffel, the symbols for a curved space, and that's going to allow us to find the actual curvature tensor. Okay, a real quick review of Christoffel, the symbols. We take a vector, which is expressed as a linear combination of its components and basis to vectors. We take the derivative of that with respect to a coordinate. Okay, we use the product rule. And now, as an example, in Cartesian space, where the basis of the vectors never change, they're constant everywhere, this goes to zero. So would just become the normal directional derivative that you're used to seeing. But as an example, in polar coordinates, the theta, the basis of the vector, is changing everywhere you change direction. So it's not constant. So you have to take that into account. And they do that in this manner. Since this is a vector, I'm taking the derivative of a vector, and derivative of a vector is a vector. You have to express that. You can express that as a linear combination of its components and basis the vectors. And this component thing turns out to be called the Christoffel, the symbol. And I'm going to leave a video link to this in the description. And there you'll find out probably more than you want to know about it. Okay, now let's shift gears and say, hey, what if this vector is in the embedded the space, so its components and basis vectors are in the embedded the space? Okay, so you take the directional derivative and you get exactly the same thing. Now, if the basis vectors lie in a tangent plane, this goes to zero. Well, what if they don't lie in a tangent the plane? Okay, so here we have just a sphere, obviously, right? We can put on here a tangent to plane like this, okay? Now imagine, but I couldn't get it to work out to make this a curved tangent plane. I couldn't do it. I'm sure you can. I don't know how. Imagine in your mind that this is a curved plane that touches at one point, all right? And there's some vector in it. Now, as that vector moves along, how do I do that? Oh, here you go. As this thing changes around in space, you see that it's going to have a component that's in that curved space. You can imagine there's some curved space here touching in one point every time it moves around. So it's going to have a component in that space, and it's also going to have a component in this normal that's sticking straight up 90 degrees. At every point, it's sticking straight up at 90 degrees. Okay. So it's going to have two components. Whereas normally we're just dealing with it in the tangent plane. Well, this is a tangent curved space. Okay. So we have to account for that. And the way we do that is to add an extra term. So you get your normal Christoffel, the symbol, times its basis vector, but we need something with to account for its projection in the normal. So this is its projection on the tangent space. This is its projection on the normal space. And since this has no indices and we have two free indexes here, we have to account for that by putting them on B. So B alpha beta is called the Gaussian curvature tensor. So there it is. Yeehaw, we found it. Now what are we going to do with it? Well, we have to get it into some format we can use it, okay? So let's take this expression and put it right back in here, right back in there, okay? So the whole thing looks like this. Now I'm going to bring this to the front. You see that? I'm going to distribute T alpha into here like that. Now look at this. I've got two sets here of summation indices. The dummy indices are called in tensor the calculus. So I got alpha, alpha, gamma, gamma. Since they're just summation indices, I can swap them. So I can change alpha to gamma and gamma to alpha, and I get this. It's totally legal to do that. All right. So that means I have a S alpha in both terms. I can factor that out. This stuff in the parentheses here is called the covariant derivative. So this is the covariant derivative of a contravariant vector component. But in this case, it's the surface covariant derivative, okay? Now, what if we had expressed that vector when we started with a covariant component and a contravariant basis vector? Well, you get the same thing. There's just a negative term in here, okay? And I'm going to leave a link to both types of these covariant derivatives in the description. If you want to know more about these, I don't want to use that time here. You can check those out, okay? All right, let's keep rocking here. Now, let's take the covariant derivative of a surface basis vector. All right. And because it's covariant here, we're going to have a negative sign. All right. And we just found this up above. It looked like that. So we can put this back in here. And look what we get. This plus this is 0. This is the negative of that. So now we have an expression of the covariant derivative of a surface basis vector is equal to the Gaussian curvature tensor times the unit normal vector. All right. And we're getting closer and closer to isolating it. Now, from way back in video number 1, where we were working on the shift the tensor, we found a relationship between the surface of the basis to vectors and the ambient basis vectors. This was just the IJKs that we were dealing with, and they're related via the shift tensor, Zi alpha, okay? So we can put this right back in here. We get this expression. We can pull this outside because when you take this derivative of this, you should use the product rule. And if we did, we'd find out that the derivative of these basis vectors is just 0. So the only thing left is this times derivative of that. That's what this means, okay? Now, from video number 2, we found a relationship between the unit normal vector can be expressed as its components in the ambient space and the basis vectors in the ambient space, okay? So we can take this and put it right in here, and we get this expression. Now we can get rid of the EIs from both sides, and we got this. All right? Now, what we're going to do here to get rid of this, we dot both sides with the covariant component Ni. This becomes 1, and we got it. So this is the Gaussian curvature, the tensor, in this format. Now, you could stop right here, use this expression to calculate this, but there's an easier way, and I learned that just today. You're taking the covariant derivative of a 3x2 tensor. So there's 3 of these and 2 of these. So that's going, and there's 3 of these. So that's going to be something like 27 components of this, and that's a pain. Okay, so way back in video number 2, the normal, we found this relationship between the components of the normal in the ambient space times the shift tensor is equal to 0. All right. So let's take the covariant derivative of both sides of this. Well, the covariant derivative of 0 is 0, obviously. Okay. We can use the product rule here. The first times derivative of the second plus the second times derivative of the first equals 0. Now we can put 1 on the other side. Now, what did we just find upstairs here? Up here, look, this is the same as that. So we can put this in here and we get this expression. So the Gaussian curvature tensor is equal to the negative of the shift tensor times the covariant derivative of the normal components. Now, there's only 3 of these here. So this is a heck of a lot easier to deal with. And we can do that. Oh, here I showed. There's something else here. Because that if I take the covariant derivative of this, I get the directional derivative like you expect, and you get your Christoffel, the symbol of the term. But because these are in the Cartesian space, the ambient space, they're all 0. So we're just left with this. All right. So now we got the simple expression that we can use. We go back up to video number 3. We get our unit normal vector expressed like this. We go up to video, oh wait, we got to do it first. Okay, so this is N1, N2, N3. So this would be the partial of N1 with respect to theta, N2 with respect to theta, N3 with respect to theta, N1 with respect to phi, et cetera, et cetera. Okay, so we take these partial derivatives. So partial derivative of this with respect to theta, this with respect to theta, this with respect to theta, this with respect to phi, with respect to phi. There's no phi here, so get 0. And here is our shift the tensor. Now we've got a 3 by 2 times a 2 by 3 will give us a 2 by 2. So we would say for the first position 1 1 and the 2 by 2, it would be this times that plus this times that plus this times that. You do that, etc., or you could plug this into a online matrix calculator, which are really nice, and you get this expression. So this is the Gaussian curvature tensor. Finally, yeehaw. Now what we're going to do with it? Don't know yet. That's what we're going to do next. All right, see you later. Thanks for watching.